So at the end of the previous video, we drew a conclusion for this particular problem. We concluded that the proportion of families that eat together 7 nights a week is now less than 38%, and we used a 0.1 level of significance in drawing that conclusion. So I want to start this video with the new question. What if, instead of using alpha equals 0.1, what if we had used alpha equals 0.05? Would we have still rejected the null hypothesis? Well, if I use alpha equals 0.05, everything in this problem would be the same except this picture. So had we used alpha equals 0.05, the P from the null hypothesis is still going to be 0.38. We're still using less than for the alternative hypothesis. The only thing that would differ is I would be using alpha equals 0.05 instead of 0.1. If I test the conditions to do this test, I would still get 264.3432, which is still bigger than 10. I would still get 0.3592, and so on. I would still get negative 1.435 for the test statistic. All of that would be the exact same, except if I'm using alpha equals 0.05, my drawing would be different. I have the normal distribution. The difference would be, though, my area in the left tail, instead of being 0.1, would be 0.05. So if that area in the left tail is 0.05, then that would change the value of my critical value. So if I want to figure out what is that value that has area 0.05 to its left, then I can do inverse norm, and I can change this to 0.05 in the left tail. And so that critical value would be negative 1.645 if I round to 3 places. So this critical value right here would be negative 1.645 instead of negative 1.28. So when I calculate my test statistic and come up with negative 1.435 compared to negative 1.645, negative 1.435 would be to the right of that negative 1.645, and so I would not reject the null hypothesis. So for this situation, if I use alpha equals 0.1, we rejected the null hypothesis. But for this case, because this negative 1.435 would not fall over here in the unusual area, my conclusion would be do not reject the null hypothesis. Well, goodness. If I use 0.1, I reject, but if I use 0.05 for the level of significance, I don't reject. Well, this shows a couple of important ideas. One, we have to choose the level of significance up front. We can't wait until we know the test statistic before we choose what the level of significance is going to be. Because if I wait until I know this value, and then I say, I think I'm going to use a 0.1 level of significance, then I'm basically saying, I think I want to reject, which is biased. And likewise, if I wait until I know this value before I choose my level of significance, and then I say it's 0.05, then I'm basically saying I don't want to reject. So we have to choose this level of significance up front before we've done any of the test. That has to be the case. Otherwise, we're biasing our test. So that's one point. The other point is, so we don't reject the null hypothesis at 0.05. We do reject the null hypothesis at 0.1. So there has to be some place in between 0.05 and 0.1 where we would switch. Like, for example, what if we had used alpha equals, say, 0.07? Would we reject or would we not reject? Well, picture-wise, here's our normal distribution. This area here then would be 0.07. So I can figure out what this critical value is by doing inverse norm of 0.07. So if I go back to inverse norm and change this to 0.07, well, I would get negative 1.476. So this would be negative 1.476. So my test statistic would be just a little bit to the right of that. So negative 1.435 would barely be a little bit to the right of that. We would not reject. But what if I had used 0.08? Well, if alpha is 0.08, then my critical value would be negative 1.405. So my picture, this area would be 0.08, and so that critical value again would be negative 1.405, and so my test statistic, negative 1.435, would be over in the unusual area, so we would reject. So again, notice that depending on the specific value that we choose for the level of significance, that affects whether we reject the null hypothesis or don't reject the null hypothesis. So there's some value of alpha that's between 0.07 and 0.08 where we switch from rejecting to not rejecting. And that value is the p-value. So the p-value. A p-value is the probability of observing a sample statistic as extreme or more extreme than one observed under the assumption that the statement in the null hypothesis is true. Put another way, the p-value is the likelihood or probability that a sample will result in a statistic such as the one obtained if the null hypothesis is true. So a p-value is the value of alpha where we switch from rejecting to not rejecting, or vice versa, from not rejecting to rejecting. Again, it is the probability of observing a sample statistic as extreme or more extreme than the one observed under the assumption that the null hypothesis is true. So if we bring back in this problem, the p-value, since this is a left-tailed test, is going to be the area to the left of our test statistic. So if I come down here, here's our standard normal distribution. So here's our test statistic, negative 1.435. If I find the area to the left of that, that will be the p-value. So I can do that by using normal CDF. We could also use the StatCrunch normal calculator. We could also use the standard normal table. I'm not going to go through all three approaches, but you could use any one of those three approaches. If I go to normal CDF, I'm going from a big negative number to negative 1.435. It's the standard normal, so the mean's 0 and the standard deviation's 1. And so this gives me this area, which is 0.0756. So this area is 0.0756. That area is the p-value. So again, that's the value for alpha where we sort of switch from rejecting to not rejecting, or vice versa, where we switch from not rejecting to rejecting. As a general rule, if the p-value is smaller than the level of significance, then we will reject the null hypothesis. But if the p-value is bigger than the level of significance, then we will not reject the null hypothesis. So if the p-value here is 0.0756, and if we're using a level of significance of 0.1 like we did originally, then we're going to reject the null hypothesis because 0.0756 is smaller than 0.1. But if I use an alpha equals 0.05, we're not going to reject the null hypothesis because 0.0756 is bigger than 0.05. Likewise, if I use 0.07, we're not going to reject because 0.0756 is bigger than 0.07. If we use 0.08, then we are going to reject because 0.0756 is smaller than 0.08. So this is going to be our p-value approach. So looking back at this page, hypothesis testing using the p-value approach. if the probability of getting a sample statistic as extreme or more extreme than the one obtained is small under the assumption the statement in the null hypothesis is true, then we're going to reject the null hypothesis. And again, how are we going to define small? Well, if the p-value is smaller than the level of significance, then we will reject the null hypothesis. But if the p-value is larger than the level of significance, then we will not reject the null hypothesis. So if we put all that we've discussed so far together, we have a procedure for testing hypotheses regarding a population proportion. Use steps 1 through 5 provided that the samples obtained by simple random sampling or the data results from a randomized experiment. If n times the p sub 0, that's the proportion from the null hypothesis, times 1 minus the proportion from the null hypothesis, is greater than 10, and if the sampled values are independent from each other, and again, the way we're going to generally verify that is that n has to be less than 0.05 times capital N, the size of the population. So that's going to be how we verify that third bullet. So this is what I said at the beginning of the first video. We can model with the normal probability as long as these conditions are met, and these are the same conditions that we used in the previous chapter for confidence intervals, because hypothesis testing again is very related to confidence intervals. So step 1, we're going to determine the null and the alternative hypotheses. The hypotheses can be structured in one of 3 ways, depending on the particular scenario. So we're going to have a null hypothesis where p equals p naught. P naught again is the specific value. And so then our alternative could be that p is not equal to p naught, that p is less than p naught, or that p is greater than p naught. So again, in our example that we've seen so far, it was p equals 0.38, and we used p is less than 0.38 as the alternative hypothesis. Step 2, select a level of significance depending on the seriousness of making a type 1 error. So again, you're typically going to be told what to use for the level of significance, but in real practice, you have to make that decision yourself, and that is going to depend on the seriousness of making a type 1 error. How much are you willing to risk making a type 1 error? Usually, we'll use 0.05 or 0.01. Occasionally, we'll use 0.1 or 0.10. Theoretically, we could use any value we want. Now, step 3. Here, we kind of split depending on if we're going to use the classical approach or the p-value approach. I'm going to be showing you both approaches for every example. So, first, we're going to compute the test statistic. So whether you're using the classical approach or the p-value approach, you're going to calculate the test statistic, z0. And so this is the formula I used in the first example. So we're going to take p hat, that's our sample proportion, minus the p from the null hypothesis, and divide by the square root of the p from the null hypothesis times 1 minus p from the null hypothesis divided by the sample size. So whether I'm using the p-value approach or the classical approach, I'm going to calculate that test statistic. Now, if I'm doing this by hand, I'm going to use the standard normal table, which is table V or table 5 from the appendix of your book. And I'm going to use that to figure out what the critical value or critical values are, depending on if I have a left-tailed, right-tailed, or two-tailed test. So I'm going to figure out, like for example, if alpha equals 0.10, and if we have a left-tailed test, then we figured out that critical value is negative 1.28. Same idea if it's a right-tailed test or a two-tailed test. Now, if we're using the classical approach, we're going to compare our critical values with the test statistic. So really, I look at it the other way around. I'm going to compare our test statistic to the critical value. So if our test statistic is either in the left or the right tail, we're going to reject. So if our test statistic Z0 is either less than the negative critical value or greater than the positive critical value, we'll reject the null hypothesis. That's what this is saying. If we're doing a left-tailed test, then the only way we'll reject is if the test statistic is to the left of the critical value, which will be negative in a left-tailed test. So if Z0's less than the critical value, we'll reject the null hypothesis. If it's a right-tailed test, we'll have a positive critical value. And if our test statistic is bigger than that critical value, then we'll reject the null hypothesis. We can state a conclusion. If we're using the p-value approach, then the p-value will be the area to the left of the test statistic if we're doing a left-tailed test. If we're doing a right-tailed test, the p-value will be the area to the right of the test statistic. And if we're doing a two-tailed test, we're going to find two values here. So the test statistic will either be negative or it'll be positive, one or the other. So we're going to find it and we're going to find the opposite. So if our test statistic is negative 1.4, then we'll also use positive 1.4 and we'll find the total area in the two tails on the outside of those two values. That'll be the p-value in a two-tailed test. So as a general rule, the p-value for a two-tailed test will be double what it would be if it was either a left-tailed or a right-tailed test. We can also use technology, and I'll show you how to do that. We can use technology to be able to figure out what the p-value is. But as a general rule, if the p-value is less than the level of significance, so if the p-value is less than alpha, we will reject the null hypothesis. If the p-value is greater than or equal to the level of significance, we will not reject the null hypothesis. And then we'll be able to state a conclusion. So we are ready to do our second example, and we're going to follow those steps, and we'll do that in the next video.